Hi, my name is Ivan Ruchkin. I'm a PhD student at the Institute for Software Research at Carnegie Mellon University. And I would like to tell you about IPL, or the Integration Property Language. This is our research on how to model and verify cyberphysical systems using multiple models. As an example of a cyberphysical system, let us consider a PowerAir mobile robot. This robot needs to go to a certain destination, but it has a limited battery. The map is known, and there are charging stations across the map. So if the robot feels like it is depleting all the power on actions like driving forward or turning, it can go and recharge at one of the stations. And of course, the robot needs to plan the whole route to the end of the mission. To engineer such a system, one can use multiple models for various aspects of it. For example, one for the mechanics of the robot, and one for low-level control, and another one to represent the power dynamics of the system. These models would not be independent since they describe the same robot and have a certain amount of overlap or redundancy. They also come with certain tools that help analyze the specifics of each model and derive useful conclusions. However, the tools may or may not work together well. And the general problem that this talk is handling is whether the system can be called safe or reliable or satisfy any other systemic property given this collection of models. And these properties would not come from individual models, but rather from the whole collection of them. And this is a difficult problem. So as an example of two models, let us consider the power-related ones. One we will call the regression power model, and this comes from running experiments with the robot and measuring how much power the robot takes for various tasks. So this is a direct abstraction of the experimental data. And one important feature of this model that will come into play later is that the turns are explicit. This means that there is a separate mode and equation for turning that was created from appropriate experiments of the robot just turning. This is a separate motion from, say, moving forward. And the other model we want to consider in this example is a planning model. It's power aware, and it plans the route for the robot to its destination. It's implemented as a Markov decision process, and it's certainly made differently than the regression power model. It also comes with a tool that can plan over Markov decision processes, or MDPs. And an important feature of this one is that the turns are implicit. So they are considered part of bigger transitions between locations, including other actions like moving forward. And this will be important later as we proceed to compare these two models. So to create an assurance case for such a system, one could make an argument for end-to-end power safety, that is, why this robot would not run out of power if it's engineered the way it is. And one argument that an engineer could create is to say that if the battery charge is greater than a certain value at each point of time, let's call this value total error, that's a given constant, then the robot will not run out of power. And this makes sense because if at any moment we're some safe distance away from the zero and all of our errors do not make us go below the zero in the battery, then we should be safe. In this case, the models are arranged as follows. The physical reality is approximated by the regression model, and the power numbers in the planning model are created from the regression model. So there is a certain relationship between the models in this case. So in this configuration, how would we get at estimating this total error? It has several components. One of them would be the error coming from the regression model and the fact that the experiments are noisy and there is a certain error due to the linear approximations of the dynamics, which inherently may be not linear. And another part of it would be coming from the planning model, and the planning error could occur because, for example, the model makes approximations or doesn't compute the optimal policy, or there is a floating point error, things like this. And yet another component there can come from the fact that the two models do not match each other, and they do not estimate the same actions with the same energies. And we will call this the consistency error. And in general, the total error is going to be some function of these three errors, maybe some additions or multiplications. This is not very important at the moment. What is important is that the total error depends on these multiple components. And in this talk, I want to focus on the error of consistency, because this is the one that is actually harder than the other two. With the regression and planning errors, there is a certain understanding of how to estimate them because they belong to certain models, and we know how to compute them, or we know how to bound them. Whereas the consistency error, no model is responsible for, and therefore we're lacking the means to estimate it, or more importantly, to verify that its value fits the certain bound. Because if we make a mistake with error consistency, we may not know the total error correctly and then actually run out of power. And one of the examples when it may happen is the following inconsistency. So as I said, the two models treat turns differently. And as a result of this treatment of turns, the energy estimates for larger missions of the robots may be off depending which turns you count and how much they actually cost. And this is one example of a threat to this power argument due to the consistency issue, which is an issue of modeling and optimizing the model slightly differently, which may be a mistake of the designer, or it may be an intentional optimization to, for example, improve the performance of the planner. So this is the kind of problems we will be handling in this talk. But let's first look at the existing approaches to them. One intuitive one and conceptually straightforward is to create a single model of all of the models and make it handle all the aspects. This way, we're getting rid of the multiplicity, and instead we reason in one place about everything. And this is conceptually nice, but unfortunately infeasible in practice, where there's many aspects and they need to be split up. A slightly more sophisticated approach could be that we decide that each aspect of the system, such as the power dynamics, is contained in a single model, and other models query it as needed. Well, clearly, this robot is not engineered like this because the power dynamics are described in both the regression model and the planning model. But in general, this is a viable approach, perhaps. It has certain downsides, like there is an extra overhead for calling other models at runtime. And also, it still may not be satisfying because even if all the calls are correct, we still don't know if end-to-end there is any error because of the interactions between the models. So this doesn't solve the problem fully. Let us look at our approach then. And here is the outline for the rest of the talk. I will look at our approach and some of the parts of it, specifically how we model the system and how we verify the properties we want. And then we will look at the evaluation, which has more theoretical and more practical sides to it. So let us start with our approach and say that the first step here in treating such inconsistencies is to specify what we call integration properties. And here is an example of it. So for this inconsistency, we could say that the difference in energy estimates should not be greater than a predefined constant. And this is the error of consistency from earlier. So what we're doing here is we're taking the vague, uncertain understanding of an inconsistency and we're turning it into a precise specification. Well, so far in English, but we will formalize it later. And the specification says that certain things should not occur. So this is a binary statement that can be checked, hopefully. And another thing here is that the statement actually doesn't say that the models are perfectly consistent. We are saying that their inconsistency is bounded. And this is another thing that is enabled by our approach. Since we say we can specify these properties, they don't necessarily say that the consistency is perfect. So this is one of the central approaches or ideas in our approach, that we specify integration properties. And so let us look at how we achieve this specification. So we have these two models and some uncertain, vague understanding of the consistency between them. So first thing we do is we create a view for, suppose, one of the models. And I will talk about views later, but let's say this is some abstraction of the structures of the model. And for the other model, we create a modal property or a behavioral property that constrains some behaviors in this model. And these are the two blocks that we use for modeling, and I will tell you more details later. But one thing to note here is that we separate the structure, which is in views, and behavior, which is described by model properties. So when we want to expose something from the model, we want to be clear what it is. Are we talking about the structure or the behavior? And various cases will make structure or behavior more convenient, and this is up to the designer's choice or the engineer's choice who is applying our integration approach. Now that we have the view and the model property, what we do is we write the integration property over them, like the one I showed before. And this integration property is a logical constraint over both the view and the model property. And this implicitly constrains the two models and gives the engineer a way to express the vague consistency property in a rigorous way. So for our example of that integration property, here is how the schema is instantiated. One of the models is the regression power model, and we will make a power view for it shortly. And the other one is the power-aware planning model. And for this one, we will write a PCTL property. PCTL stands for the probabilistic computation tree logic. And this is a logic that can constrain executions in an MDP. And then the integration property will actually be written in IPL to co-constrain the view and the PCTL property. So IPL as a language follows several design principles here. One is expressiveness. We want to be able to express complex properties that mix structure and behavior, and this is non-trivial because usually it's either one or the other. Then we want the models to stay modular. That is, we don't want to create a single mega model and analyze that because it doesn't fit the tools. It does not let us reuse the tools that come with the models, and that constrains too much the disciplines that contribute to the development of cyberphysical systems. And finally, we want the analysis of the statements in IPL to be tractable. That is, that in practice, the running time of the verification should be reasonable and it should terminate eventually. And one of the blocks, as I said, that IPL builds on is views. This is static abstractions of model structures. And one of the reasons why we use the views is that they're specified in a way that make it easy to run SMT solvers on them, or generally constraint solvers, because they are hierarchical discrete structures, which SMT solvers do well with. And then on the other end, we have behavioral properties, and this is formulas and model logics, PCTL, LTL, or others, and they constrain model behaviors. And this is how we deal with the perhaps more continuous behaviors or just more messy ones that are difficult to expose as discrete structures. And one of the added benefits here is that many models come with model checkers, and they can verify the properties about these models. So we get the verification here for free. We don't actually need to write a separate tool for the behavioral properties. So these are the principles behind IPL. And let us go first into the details about these two modeling blocks, views and behavioral properties. So with the power model, we decided to create a power view, and this is a design decision. It is not always like this, but we decided to make it a library of atomic tasks. That means that for a given map, there are neighboring locations, and for example, moving from location 1 to location 2, if they're neighbors, is an atomic task. And on a given map, all these tasks are defined and there's a finite number of them. Or for example, turning from one direction to another. Given the map, we can actually automatically generate this power view, which is a nice bonus to automation. And so the idea behind the power view is that the atomic tasks can be combined to form more complicated missions where a robot goes through several locations, it charges and does other things. And to, of course, form valid sequences, we need to use extra constraints. And this is where the SMT solvers come in and help us instantiate and give examples of such missions. And how we model each task, it is a component in the architecture description language. We use ADL in this case, but really any architecture description language can work. And each task forms a component and then can be connected with connectors. Each task also has properties, in this case, start, end, energy, time, and so on. And the energy numbers here come from the regression model. And this is how the view serves as an interface to the regression model. It creates these structures for which it calculates the energy predictions. And that is how we expose the energy dynamics from the regression model. So let's look at the actual power view. Here's what we have. We have a number of declarations of processes. These are tasks moving from, say, location 7 to location 6. and this is straight moving tasks. And then there is the rotation tasks. For example, rotating in location 2 from the direction of location 3 to the direction of location 3. Well, that would be an empty task. Or from the direction of location 3 to the direction of location 8, that would be a non-empty task. So the components are declared, and then also the properties are specified, such as start and the heading or direction that the robot is facing, and then the energy, and these are the numbers that come from the power model. And this is stored in the view. So this is how we deal with the views in this case. And again, in other cases, the view can be completely different. This is where there is certain openness to the design. Now let's look at the behavioral properties. And in this case, as I said, we are specifying them in PCTL. And Prism is the tool that can verify them. It's a model checker for MDPs and PCTL properties. And the properties here are written manually, but they're not big, so that's not a very big problem. Let's look at an example of a property. Maximum probability of the robot finishing the mission of 3 moves, straight, and then turn, and then straight. And in this case, this is not a binary statement. Prism can also execute queries. So in this case, we're querying the maximum probability of completing such a mission. So here's how it's encoded. This is the Prism property language based on PCTL. Let's walk through this. We have on the left the probability operator, and then we have the LTL formula with untils stacked together, and it's saying that the location of the robot, which is a dynamic variable, and that's why the underline is here. This indicates that this is a behavioral variable, and it says that it refers to T1 start, then T2 start, then T3 end. And then there is an extra clause that says that eventually the location has to be T2 start, because actually under the semantics of until, the robot can skip T2 start and just go from T1 start to T3 end. So we don't want this to happen, hence the extra clause. And so this is an example of behavioral property that is being used as an interface with the planning model. Instead of exposing some of the behaviors from the planning model, we instead constrain them with this property. And we didn't have to invent the language. This is an existing language, and we're just reusing it along with a model checker that can check some statements. But the idea is using these properties to interface with models. So now that we discussed 2 building blocks on which IPL stands, let us look at the syntax and how it enables interleaving them. So in this diagram, I don't want you to read into the details, but just to give you the general sense of how the syntax works. So we have the yellow terms, also known as rigid. They're associated with the views, and they can be checked with model checkers. And this is variables, constants, or for example, the component.property construct, which you've seen, such as T1.start. All of this can be checked by the SMT solver based on the views that we have. But now we want to integrate it with the behavioral languages. And this is tricky because we both want these formulas to refer to behavioral languages and behavioral languages to embed the rigid things. And this is the green part, that is the flexible part, and that is much more customizable in our language, hence the plugin points here. For example, we can say state variables, and this is where each model can plug in its own variables, such as the robot location, and use them in the language. And then there is model atoms, which is where we plug in, for example, the modal operators like until or eventually. And then there is model instantiation that indicates the initial parameters of the model, which you'll see shortly. And once these 2 are in place, we actually combine them in formulas where we add quantification over these variables, and like T1, T2, and T3. And this is great because it becomes very expressive and allows us to specify a whole lot of things, because the variables are quantified and they can have arbitrary values from the domain of quantification. And this way, for instance, we can talk about missions of any fixed length using the variables for each step of the mission, and then put in the appropriate constraints in the rigid part, and then constraining the behaviors in the flexible part. So let us look at one of the integration properties in IPL. So this is one, and I know this is a lot of detail, so we will step through it. The first, the rigid yellow part, says that for any 3 sequential tasks, T1, T2, and T3, that form a straight turn straight pattern, so the second task is a rotation, and they have ends and starts aligned appropriately, and they have sufficient energy, which in this case means that it fits in a battery so that the robot can actually make this mission happen. So we're saying if this is the case, then it implies that the execution in the planning model with the probability of having done this mission, and this is the formula that we saw a couple of slides ago, initialized appropriately. So this is the model instantiation operator here that assigns certain values to the initial location, the goal location, and the initial battery. And this is where the error of consistency comes in. We're saying that the initial battery is initialized by the regression model's prediction of the energy expenditure of the mission, plus the error that we're willing to tolerate for the integration of these two models, equals 1. So this means that the planning model will return the probability equaling to 1. That is, the planning model does not run out of power either. So again, the big picture is, if the regression model thinks that the mission is power safe, then the planning model should be able to make this mission happen, modulo the consistency error here. So that's why we're giving the power model slightly more energy in case there is a small inconsistency. And of course, if there is a bigger inconsistency, then the probability won't be 1, and this will fail the property. So this is how we specify things in IPL. And this is how we express the vague intuition about the consistency relationship between the models. And now let's look at how to verify this. And so this is a complex process, so bear with me here. We start out by having the views in the models that contribute to certain IPL formulas. So in this case, we would have the power view and the behavioral model of the planner. We don't actually need the regression model. If we created a view of it, we can forget about it for a moment and simplify the picture. So the first step here is to massage the formula a little bit. First, we put it in the pre-next normal form. That means that all the quantifiers are in the beginning, but they were already in the beginning. And then we actually remove the quantifiers and replace the quantified variables with free variables. And then what we do is abstraction of subformulas, the green modal part of it. And let me explain. There's actually two abstractions that we do. One is the functional abstraction. So we replace the green part with a function of those variables. And then there is the constant abstraction where we replace the green part with a constant. Both the function and the constant are uninterpreted from the perspective of the SMT solver, I guess, at least. And the idea here is, with these two abstractions, is to try to compare them. Specifically, when we call this phase saturation, we compare when the abstractions don't match each other. And this is important because what we're really doing, intuitively speaking, we're saying, so suppose we don't know anything about this green part because it was plugged in and SMT solver actually cannot reason over it. We're saying, what are the cases, what are the missions when it will be necessary to reason about this green part? Or in other words, what are the cases when, if we take the result of this green thing as a function of these variables versus when we just consider the fixed value, when will we be able to not match them? And this is the task we're given to the SMT solver, to find all such missions or all such values for these free variables. And the SMT solver saturates the value, so it finds all the possible values here. And then the next step, also time consuming, just like saturation, is model checking. Now that we know these potential missions where the robot may run out of power depending on what the planner does, we instantiate the planner for those missions and we model check, and we see what is the value of the green part, or in this example, what is the probability of the planner making it to the end of the mission. And once all of this information is collected, we can do the final check. We do it using the SMT based on the functional abstraction, but we are also joining all the interpretations from the model checker for this function. So now it's not just some uninterpreted function, but we also know its value on the missions that matter. And this is just enough information for the SMT solver to decide if this formula is actually valid or not. So this is the overall algorithm, and there's of course more details in the paper, but I hope this gives you an intuition of what we're doing and how we're using the SMT solver and model checkers collaboratively to tell how much model checking we need and then do it and then resolve the formula. So with this, let's transition into the evaluation of our approach, starting with the more theoretical side of it. We do have a theorem formalized and proven in the paper that if this final check, the last step of the algorithm, says that the formula is valid on those interpretations that we collected, that will happen if and only if the formula is actually valid according to the IPL semantics, which are, by the way, also in the paper. And the implication of this is that if IPL verification returns some answer, this would be the correct answer. So if it returns something, you can trust it. The question is, of course, does it return it or does it terminate? And theoretically, we cannot guarantee termination here because we have uninterpreted functions, we have quantifiers and the full complexity of the first order logic, so we don't know if it terminates. But in practice, if you model it smartly with finite views and finite quantification domains, so you don't quantify over integers, say, it does terminate. We've never had a situation where it wouldn't terminate because we're quantifying over the views largely. So that's it with the theoretical part. Let's look at the case study. And it was actually based on the real project with the mobile robot that implements this power-aware algorithm on the robot. And what we did with this project is we reviewed the artifacts from a previous phase of the project so that they're not changed. It's an existing implementation, and we're verifying it without biasing it by trying to re-implement it ourselves. And we reviewed all kinds of models and relationships between them to see where they can be model integration issues. But we ended up focusing on the power models just because it became such a big aspect of the system that it spilled over many of the representations of it. And what we did specifically, we formalized three constraints on the consistency error. One of the ones we saw with the property that said, if the regression model is power safe, then the planner is power safe. And then we also formalized it the other way. If the planner is power safe, then the regression model is power safe. And then we did the two-way constraint that they declare missions either both power safe or both not power safe. So these were the properties that we studied here. And actually, with all the variations in the missions and the maps and models, we ended up with over 120 IPL properties, and we ran verification on all of them. So this was a substantial effort. And we did discover inconsistencies in the actual models of this robot that were not caught by other methods like testing. I want to tell you one example of an inconsistency that we discovered. And that one was that the planner does not actually check if the battery is enough to make a certain step. The way it looks in the planner is like this, that it says that the battery in the next step should be the maximum of the current battery minus the required energy of the step, or zero. And most of the time it works because the battery is plentiful and we just subtract the energy. And it also works if we run out of energy too early because we just set it to zero, and then the planner knows that we ran out of energy and it stops that branch of planning. So this is all fine, except in the very last transition, you can actually make it happen without having enough energy, because if the battery is 10 and the required energy is 20, what you're going to have is battery 0, but you will have made the transition. And so the planner would consider it a successful mission. And this is an issue, because some plans would end up being too aggressive, and the planner would suggest them, even though in reality they would lead to power running out in the very last step of the plan. And this is a problem. And the fix is pretty straightforward. It's just about checking the battery being more than 0 in the final state, or checking if you have enough power, which is equivalent here. But it wasn't done, and that was an issue that threatens our consistency error, and that threatens the whole power safety argument. And there are other inconsistencies we did catch, and we also studied the performance of IPL verification, and this is all can be found in the paper. Let us now just summarize the case study and see what are the implications. One of the questions we asked is, what do integration properties look like in practice? Do they occur? And yes, they do occur. And in our experience, they occurred as an implicit step in an end-to-end safety argument. Usually it would be assumed that the consistency error is zero. But in reality, it turns out it may be non-zero, and if there is a consistency issue, that it might be very much non-zero, and that leads to the safety violations of the system. Then, can we specify it in IPL? Yes, with some view modeling and using the existing behavior languages, we can actually combine them to specify such complicated integration properties in IPL over multiple models. And then what about the performance? Is the implementation tractable? And yes, it was. The properties terminated depending on their complexities from under a second to up to 2 days, but that's for a very complex property of a very big model. But the remarkable thing here is that IPL itself adds very low overhead, not more than 2% and usually less than 1%. The rest of the time is spent by the SMT solver, which is an existing tool, and the model checker, which is also an existing tool. So largely the performance improvements here would be coming from improving the existing tools. Our approach has certain limitations, of course. One is that the integration properties are often complex and they're very contextual. They're tied to the specific models and their relationships. And to write them, one has to have a very good understanding of them. So an engineer that only understands one model might not be able to write an appropriate integration property. And of course, if you're talking about some new pair of models, you have to write it again. But that is just the nature of integration. And then we also need views for our approach to enable SMT checking. And then that means that we need to model them and design them, and in certain cases might not even be able to automate them. But this is the price we pay for running some complex verifications, that we need some modeling support for it. And so this is also not unexpected. And finally, this particular implementation was not exactly made optimal. SMT solving could have been incremental. Right now, it just solves every case from scratch. And then the model checking, once SMT is done, could actually be made concurrent because there is no information flow between the different model checks. And that could lead to huge performance gains in this case, which has not been done. So this is our future work. Now let me summarize the talk. We studied relationships between multiple models in cyberphysical systems, and we discovered that these relationships can be complex and they can affect arguments for safety of the systems. We proposed an approach that is based on views and behavioral properties that are linked together in integration properties specified in IPL, and the syntax smartly enables interleaving both structure and behavior there. We also applied it to a case study on a mobile robot. But our hope is that the approach is general and actually applies not just to power and not just to MDPs and not just to robots. And the general implication of this work is that now we don't have to guess any consistency relationships, and we have a tool to specify complex integration properties rigorously. And then engineers can also work within the constraints of their own models without bothering to create the supermodels. And as an extra bonus, we also have a way to now verify those very complex properties that involve multiple models. This is all I had for you. Thank you for listening. Bye.